Hi guys, welcome back to alGOds. So today we are discussing one more interesting question of HackerRank, that is Sherlock and MiniMax. So let me just explain the question. In the question, Watson gives Sherlock an array of integers. Given the endpoints of an integer range, so we have given the endpoints of an integer range for all m in that inclusive range, determine the minimum. So minimum is going to be absolute difference between array of I and m for all I lies between 1 to array.length. Once that has been determined for all the integers in the range, return m which generated the maximum of those values. So once all the minimums has been determined, we are just going to return the m which generated the maximum of those minimum values. So if there are multiple m's that result in that value, return the lowest one. So this is our question. I know the problem statement is a bit confusing, so let us understand with the help of example. So this is our example array. So array is going to be 3, 5, 7 and 9 elements present in the array, and this p and q are the endpoints. So p is 6 and q is 8. Now this is our m. So values of m are 6, 7 and 8 respectively, and here we have calculated the absolute differences. For m equals to 6, absolute differences are 3, 1, 1, 3, and the minimum is going to be 1. For m equals to 7, absolute differences are 4, 2, 0, 2, and min is 0. Similarly, for m equals to 8, absolute differences are 5, 3, 1, and 1, and min is 1. Now our goal is to find the maximum in these minimums. So maximum is 1 in these minimums, and there are two ones in the minimum. So first one corresponds to m equals to 6, and second one corresponds to m equals to 8. So here it is written, if there are multiple m that results in that value, return the lowest one. So we need to return the lowest one, that comes out to be 6. So our answer is 6. So here are the constraints. So first constraint is n represent the number of values present in the array. So there are total number of 10 is to the power 2 elements present in the array at most. So array of I represents the value of an element in the array, and the range is 1 to 10 to the power 9. P and Q are the endpoints, and the range is 1 to 10 to the power 9. So these are our constraints. So the first basic approach that crosses our mind is brute force approach. So brute force approach. So what we are going to do in the brute force approach? We are just going to take a for loop from P to Q, and we are going to take another for loop for the array, and we are just going to calculate the absolute difference between array of I and m. And if this distance difference is minimum, then we are going to store it in array of minimum, and then we are going to just iterate over this minimum array and find the maximum value and return the corresponding m value to that maximum value as our answer. So this is how we are going to do the brute force approach. So total number of operation in the brute force approach is going to be, we are going to take a loop from P to Q. So our range is from 1 to 10 to the power 9. So 10 to the power 9 multiply by, we have taken a loop for array also. So at most 10 to the power 2 elements multiply by 10 to the power 2. So they are at most 10 to the power 11 operations. So it gives us TLE, time limit exception. So we are just needed to optimize this approach. So let's discuss the optimized approach. So before discussing the optimized approach, what is our goal? Our goal is to maximize our minimum values that are absolute difference between array of I and m, and my I lies between 1 to n. This is our goal. So is it efficient to take all the m's in the from P to Q and find the absolute difference? No, it is not efficient. So what we are going to do, we are just going to take only those m's which are which maximizes our minimum values. So we are just going to take those m which maximize our minimum values. So let's understand this statement, what this means. So let me just draw a number line. Let's take this is our number line, and a1 and a2 are the two elements of an array. Now we are going to consider that the points between a1 and a2 lies in the range from all the points in the between a1 and a2 lies in the range p to q also. So now let's say the distance between these two are x. Now there is a point that m, that is variable, and we can say iterator of the range from p to q. Now this distance is m minus a1, and this distance is a2 minus m. So these are the two distances. Now what is our goal? Our goal is to maximize our minimum of m minus a1 comma a2 minus m, and here my m lies between a1 to a2. So this is our goal now. So let's say if my m is at a1, my distance is 0, my minimum is 0. If my m is here, my minimum is this one, and my minimum is greater than the previous one, so it is maximized. If my m is here, my minimum is this one, and my minimum is greater than the previous minimum, so yeah, my minimum is again increased. If my m is here, my minimum is this one, and it is greater than the previous one, so it is increased again. So my minimum is increasing till a point, and afterwards it get decreased. So let's see that thing also, what that means. So let me just draw another number line. So these are the 2 points a1 and a2, and let's say this is the midpoint. Now if my m is at a1, my minimum is 0. If my m is here, my minimum is this one, so it is increased, or we can say greater than the previous min. So yeah, my min is maximized. If my m is here, my minimum is this one. If my min is here, my min is this one, and it is greater than the previous one. If my min is at the mid value, then my minimum is this one, and it is greater than the previous one. Yeah. Now if I take a m at the right hand side of the mid, then my minimum is this one, and my min is decreased from the previous min. So now if my min is this, m is this one, my min is this, and it is again decreased. If my min is m is this, my min is again decreased. If my m is at a2, then my min is 0 now. So at which point my min is maximized, or we can say maximum value of m, maximized or minimum value. So at m, or we can say at mid, my minimum is maximized, it is greatest. So now we are going to consider my m as mid, because this m maximize our minimum values. So I hope now you get what this means, maximize our minimum value. We are just going to choose only those m which maximize our minimum values. So that m is mid value. So let's see it with a graph also. So now these are the minimum values, and this is the points. Let's say this is a1, and this is a2, and this is mid. Now if my m is at a1, my min is 0. If my m is at here, my min is, let's say, here. If my m is here, my min is here. Let's say my m is here, now my min is here. Similarly, if my m is here, my min is now decreased. Similarly here, my min is again decreased. So we can clearly see that thing, that at m equals to mid, my minimum is maximized or greatest. So we are going to choose m as mid value of two adjacent elements. So let's write the algo. So firstly, what we are going to do, we are just going to sort the array. Second, we are going to take mid as m, because it maximize our minimum values. So we are going to take m, or mid as m, because because it maximize our minimum values, and we are going to take adjacent elements in the array and calculate the mid. So let's see. Let's say this is our array x1, x2, x3, x4, x5, and x6. So these are our elements in the array, let's say. And what we are going to do, firstly we are going to sort. Yeah, so now it is sorted. Now we are going to take these two elements, find the mid, let's say mid 1. Now we are going to check if my min is maximized or not, or greater than the previous one. If it is greater than the previous one, then we are going to store mid 1 in our answer. Now we are going to take these two elements and find the mid, let's say mid 2, and finding the min again. If the min is greater than the previous one, we are going to store the mid 2 as in our answer. Similarly, for these 2 points, we are going to calculate the mid, let's say mid 3, calculate the min. If this min is maximized from the previous one, or we can say greater than the previous one, then we are going to store this mid 3 in our answer. Similarly for x4 and x5 and x5 and x6. So this is how we are going to check. Now the only thing left is the boundary condition. So let's discuss the boundary condition with the help of an example. So let's take an array. So the elements in the array are, let's say, 5, 7, 9 and 13, and let's say the range is going to be 1 to 20, let's say. So this is my P and this is my Q. Now firstly we are going to sort the array. Since the array is sorted, first step is completed. Now second point is we are going to take the elements in the pair as adjacent elements, and we are going to find the mid. So mid comes out to be 6 now. Initially my min is 0. Now we are going to calculate the min. Now min comes out from the mid is going to be 1. So now my min is 1. Is it greater than the previous one? Yes, it is greater. Now we are going to store this mid, or we can say this m, in our answer. So this is our optimal m, we can also say. So we are going to store 6 in our answer. Now what we are going to do, we are going to take these two elements, calculate the mid comes out to be 8. Now from 8 we calculate the min comes out to be 1 again. Since is it greater than the previous one? No, it is not. So we are not going to do anything, we are just going to proceed further. Now we are going to calculate the mid for these two elements. Mid comes out to be 11. Calculate the min comes out to be 2. So it is greater than the previous min. Yes. So now what we are going to do, we are going to store this mid in our answer. So my answer comes out to be 11 now. Now what we have forgotten the two things. That is, if my left end, that is P, is smaller than the smallest value in array, then m equals to P is also a valid candidate. It can also maximize our min. So we are going to find the min from m equals to P also. So finding the min from m equals to P, P equals to P is 1. So 1 minus 5 gives me 4. So my min is maximized because my min is greater than the previous min, that is 2. Yeah. So now what we are going to do, we are going to store this m, or we can say this P, in our answer. So my answer is going to be now 1. Similarly, another condition is if my right end, that is Q, is greater than the largest value in array, then we are going to take m as Q also, because it is also a valid candidate. It can also maximize our minimum value. So my Q is 20, and 20 minus 13 gives me 7. So my min is going to be 7. Yeah, it is greater than the previous min. So now it is maximized. So we are going to store our answer as Q. So my answer becomes Q. So these are the two boundary conditions that we have forgotten. Now let's write the algorithm again. So first point is sorting. Second point is calculating the mid of adjacent elements of sorted array. That is our optimal M. Third point is checking the condition if my left end, that is P, is smaller than the smallest value in array. If it is true, then what we are going to do, we are going to take our M as P, and we are going to check if my min is maximized. If this is true, then we are going to make our answer as P. Otherwise, we are not going to do anything. Else we are not going to do anything. Similarly, if my right hand, that is Q, is greater than largest value in array, then what we are going to do, we are going to take MSQ, and we are going to check if my min is maximized or not. If my min is maximized, we are going to store q in our answer. Otherwise we are not going to do anything, and we are going to return our answer as it is. So this is our algorithm, and we have done this in O of n log n time complexity. So I hope you got the solution, and the code link is in the description, and thank you for watching.